On the other hand, let's see if I change the boundary condition. If I switch the boundary condition, not that it's actually a known value, but if the boundary condition is actually Neumann. So let me say Dirichlet boundary condition. Boundary condition means my solution 0 is equal to a given value, right? W0 given. So that's what causes us to have the beginning and the end of the matrix to be simply truncated. It's because if you apply the numerical scheme W at I equal to 1, Wi plus 1, which is W2, plus W0 minus 2W1 equal to, equal to minus F. Sorry, this is 1 minus F1, right? You actually move the known value to the right hand side. It becomes W2 minus 2W1 is equal to minus F1 minus W0, right? These are the known, these are the unknowns, and the coefficients are minus 2 and 1. That's what's over here. Sorry, I think I forgot to divide by delta x. So this is actually 1 over delta x squared minus 2 over delta x squared, and there is also a delta x squared over here. But if I have a different boundary condition, let's say the Neumann boundary condition, so that's just different names people give for different type of boundary conditions, is actually the derivative of the solution at x equal to 0 is a given value, right? So let's say V0, okay? So if this is the case, what I have is actually a little bit different. So what I have is one of the way to discretize it is that I'm going to be discretizing this using Wi plus 1 minus Wi minus 1 divided by 2 delta x. We know it's a second order approximation, right, at I equal to 0, which means this is equal to W1 minus what? W minus 1 divided by 2 delta x. All right, so this looks actually weird, but then consider I also have a similar equation plus f at 0 is equal to 0. So that's our differential equation, right? So if you look at the differential equation, what I get is the discretization of the differential equation at I equal to 0 give rises to that. Right, so this is again equal to 0. Now combine these two equations, we can successfully cancel this Wi minus 1. Right, how do we do that? We can substitute one of the equation into the other. So the first equation gives W minus 1 is equal to W1 minus 2 delta x times V0, right? So that's just from V0 equal to that. And now we plug this in, we get a 0 equal to, okay, so now Wi minus 1 is replaced by that, and this part is known. So I'm going to be combining known and unknown later on. W1 minus 2 delta x V0 minus 2 W0 dx squared plus F0. So combining known and combining all the knowns, which are this is known, this is known. Remember now W0 is actually not known, right? We only know the derivative, not the value. So W0 now becomes an unknown as opposed to a known. And the unknown, let's write on the left hand side, I have 2W1 minus 2W0 divided by delta x squared would be equal to, let's see, the delta x cancels, 2V0 divided by 1 delta x, right? and minus f0. So that's my differential operator. Yes, question? Pardon? W minus 1 represent the value of W at what we call the ghost grid point. Right, so this is the domain 0 to 1, and these are the internal grid points to delta x, and you can imagine there is also a grid point at minus delta x, and the value at minus delta x is W minus 1. Right, so it's kind of the extension of the solution into the negative part of the axis. Right, I applied actually the PD only over here. Right, so basically what I'm doing is I'm actually applying the boundary condition at x equal to 0. I'm also looking at the PD at x equal to 0. It's just the PD at x equal to 0 uses the neighboring grid point, which is at x minus 1.
Why don't you just use the forward scheme or the condition?
You can use the forward scheme. We can talk a little bit later. So there are multiple ways of discretizing the boundary condition. Right, so one of the ways to discretize it is actually just to use the internal points, and you're going to be getting a scheme that is different from what we are discussing here. So here I am introducing a different way of discretizing the boundary condition. That's the so-called using of the ghost points. And the idea of the ghost point is that you can write down more than one equations, right? So you can write down more equations on the boundary because of the boundary conditions, right? So you can write down both the discretization of the partial differential equation and a discretization of the boundary condition at the boundary, and both the discretization of the PD and the discretization of the boundary is going to involve some grid point beyond the boundary. And it turns out even though both equations involves this ghost point, the fact that you have more equations actually helps you cancel out the ghost point, so that the ghost point would no longer be unknown. Right, so in solving the differential equation, you actually don't use the ghost point, but like the ghost point would actually appear only in the derivation of the numerical scheme. Right, does it make sense? Okay, so here is one example, is that we actually use the ghost point over here, and the ghost point is involved in discretization of the boundary condition. It's also used in the discretization of the internal PDE. But then we substitute the discretization of the boundary condition into the PDE, and then the ghost point disappears. And we have just a scheme involving W1 and W0. Both are inside the domain, right? W0 actually stays right on the domain, W1 is inside the domain. Did that answer your question? Yeah, okay.